So in this video, we're going to be discussing a fundamental concept in chemical engineering, which is that of material balances. We shall begin by stating the general formula or equation that a material balance follows. That is input, so in, minus the output, out, plus any form of generation, gen, minus any form of consumption, con, is equal to the accumulation, acc. So looking at these terms, the input is any mass entering our system through our system boundaries. The output is any mass leaving the system through our boundaries. Generation and consumption will always occur when there's some sort of reaction. So if you had A forming B, there would be generation of B, but consumption of A. So that's where those two terms come from. If you have a reaction, so say you're balancing material across a reactor, you'll have your input mass, output mass through the outlet stream if there is one, and your generation minus consumption term would represent any sort of reaction that is taking place. The final term, accumulation, is an interesting one because quite often this term can be equal to zero, but is quite often represented by a derivative with respect to time. And in chemical engineering, we normally say that when acc is equal to zero, so when there's no accumulation, this implies that we are at something known as steady state or steady state conditions. What steady state means simply is that any derivative with respect to time will be zero. So it means that there's no accumulation in the system. So no mass is accumulating in our reactor, for example. Steady state is one of the most fundamental assumptions you can make when completing a chemical engineering problem, and it quite often leads to significant simplifications because, as you can imagine here, if this is zero and this is zero, then essentially all you're left with is in equals out once you've taken the out across to the right hand side. So simply, if we were to consider what sort of dimensions these terms have, normally we're dealing in terms of kilograms per time. So that could be kilograms per second, kilograms per hour, kilograms per day. But we can also write it in terms of mole or number of moles per time. So drawing on our knowledge of chemistry. But it's important to note that quite often in chemical engineering problems, you may be given a volumetric flow rate, something along the lines of liters per time or meters cubed per time. But it can be difficult to use this formula because quite often volumes aren't additive due to changes in density. So more often than not, if you're going to use this equation, you'll be dealing with quantities given in kilograms per time or moles per time. But pretty much everywhere in chemical engineering, it will come back to this equation in some form, especially when you're looking at materials within a process, for example. Okay, so using the formula that we've just discussed, let's consider a very, very simple example, which is simply, we're not going to go into mole fractions or anything like that, just simply a case where it's steady state like we mentioned before, so there's no accumulation, and we have one inlet and two outlets. So let's imagine we have our unit here. Doesn't matter what it is, could just be a splitter in this case. We have our input here, and we have our first output here and our second output here. For convenience, let's call this one stream 1, this one stream 2, and this one stream 3. And let's say in stream 1 we have 100 kilograms per hour of material coming in, and in stream 2, let's say that stream 2 takes 70 kilograms per hour of that material. Well, we've said before we're considering steady state, so let's go back to our original equation that in minus out plus gen minus con equals acc. So we're assuming there's no reaction, so there's no generation and no consumption, they're both zero. And as we've said before, we're making this steady state assumption, which means that we can say our accumulation is zero, which means our material balance equation reduces to in minus out equals zero, and further in equals out. Well, now the question is, how do we relate this to our problem here? Well, it's rather simple actually, because what's coming into our system, the only stream coming in is stream 1, and in, therefore, in this case, is 100 kilograms per hour. Out is going to be the flow rate of stream 2, so 70 kilograms per hour, plus this unknown flow rate of stream 3, this question mark. But now this is simple. We have our one equation and we have one unknown. So substituting this into here, we get our in, 100 kilograms per hour, equals out, which is 70 kilograms per hour, plus our question mark, kilograms per hour, which means that our solution in terms of finding this unknown flow rate here is simply to make this term here the subject of the equation, which is simple enough. 100 minus 70 is 30 kilograms per hour, which would be the answer in this case. One thing that's important to note with problems like this is always to make sure that the time unit is consistent throughout. So for example, over here, if this had been kilograms per second and this one here was kilograms per hour, well, when substituting into our material balance, just always make sure it's consistent and that the time unit is the same throughout. But yeah, following this method, simplify the material balance first, substitute in what we know, rearrange for the unknown, and you will yield 30 kilograms per hour. In our next video, we shall consider what happens if stream 1 is composed of multiple species and how we can then find the flow rate of these species in streams 2 and stream 3, and also delve more into what is known as a degree of freedom analysis, which is a tool that we can use to determine whether or not the problem is solvable in the first place. In this case, we sort of alluded to it here, where we said that we had our one equation here and our one unknown here. So a degree of freedom analysis is essentially number of equations minus, or number of unknowns minus the number of equations you can write. And if the DOF is equal to 0, then it's good. It's solvable. In this case, that was fairly trivial because, you know, one equation, one unknown, the equation being the material balance. But in a few videos' time, we shall consider an example where potentially the degree of freedom is not equal to 0, and what happens then. Thank you for watching, and I'll see you in the next video.